Now, iterative method, I will cover, in fact, several of them. So let's start with first Jacobi method. Okay. So what is Jacobi method? So this equation I already wrote. No, phi I comma j is 1/4 this. But this will be phi under steady state, or when for the real solution. So what we do is we start with random guess. Okay, you just start with you just fill up the grid with guess values. Okay, you just, of course, the boundary condition is specified already. So this you have to set the boundary condition appropriately. But inside will be, you just put guess value, which is, you kind of know the solution somewhat. Okay, and then, well, you don't know the exact solution, but you know that, well, if I put a potential V here, then I know that I'm 0 here, potential will decrease if you go towards the right. So we can choose somewhat, don't put a random one, but you choose decreasing function. Even if you put random, it will converge. It's guaranteed to converge. In any case, the idea is that for every point I comma j, I take the 4 neighbors like that and average them, and I get 5. So I can do a loop. So for every I comma j, I just compute these things. I compute the average. So this will be a new array, and I just compute that for every grid point. And once I updated it, then I replace phi by phi bar. Okay, and loop again, and keep doing it until phi bar minus phi maximum. So it will be function of grid. So you look at max, is it less than some tolerance limit epsilon? Once I reach this limit, then I stop. I say, well, the phi bar is a good approximation to the potential. Okay, so this is a snippet of the code. Here my boundary condition is 0 everywhere, 0 in all other walls, V in the left wall, V 0 comma colon, like here x coordinate is 0, so that is this one, and colon all y. Okay, so this is that wall, this wall, that is V, and rest all is 0. So I first set up my grid, m plus 2 and n plus 2. So my unknown things are inside. Okay, so that is n comma m, but I have 2 values for left wall and right wall, and top wall and bottom wall. Okay, so these two correspond to them. Now, if error is greater than epsilon, I'm going to show you what is error a bit later. So yp, we can do vectorized operation. No, you don't need to do a loop. Don't loop for this computation. So we do the vectorized operation 1 colon n plus 1. Okay, so I start with 1 up to n plus 1 along x direction. Y direction is 1 to m plus 1. Go in the vertical direction. Okay, so this one is average. Okay, so first compute the sum. So this is shifted 1 to the left, right? So it is 0 colon n. So this was shifted to the left. Whole grid shifted to the left. Then this is whole grid shifted to the right. So that corresponds to this one. This whole grid is shifted down, and this whole grid shifted up. Okay. So first compute the sum, then divide by 4, and this is my y prime, y bar actually, and then I compute error as yp minus y. Okay, so this difference of yp minus y, and compute the max, absolute and max. Okay, this is absolute and max, and after that we copy yp into y. Okay, so we copy into that and see whether error is less than epsilon. So we continue the loop until error is greater than epsilon. Okay, so this is what we do, and we get the answer. So I don't remember, the potential probably is 5 in the left. I don't know. So it's non-zero here, and this yellow strip, and is 0. So we can see this thing. 0 is purple, and red is 1. So my potential in the left is 1. So you can see the potential is decreased. Well, of course, 0 is this side as well. Okay, so that's why this potential is looking slightly complicated. So if we draw the contour, we'll be decreasing, and finally we get zeros towards the edge, all the edges. Okay, so this is the potential. This is a density plot. Okay, and it, of course, you get this after some time. Okay, so let's look at how does it converge. So maximum error. Error will, in the beginning, error will be a lot, right? Because the difference will be 1. This is 1 and 0. So the difference will be 1. Okay, max difference. But later on, once we get the solution, the difference reaches something like 10 power minus 7 or so here. So these are around 2000, no? 2000 iteration. So around 2000 iteration, we are getting the error to come down. Okay. So I have a table where I list the number of iterations required, 10 power minus 6. Okay. So this is Euler, not Euler. Yeah, this is a Jacobi, so not Euler, Jacobi method. Okay. I'm going to describe these two in next slide. Okay. So next method is Gauss Seidel. So what do you do in Gauss Seidel? Remember in Jacobi method, I was creating a new array, y prime or y bar or phi bar actually, right? And then new array and getting the difference. But Gauss Seidel, the Gauss was same Gauss. Okay, I mean he noticed that when I'm advancing in going like this, so let's say I'm here. By the time I reach here, I already have updated the files for these values. All these values have been already updated. These are updated already. So why not use the updated files when I compute phi for this? In Jacobi method, I was using phi of the past for every grid point. Okay, it was done in a vectorized operation, but it was using old values to get phi at every point. But Gauss Seidel says, well, update phi here using the new values of phi, wherever new values are there. When new values are not available, you use the old values. So when I come here, I should use, when I come here, I should use all the phi's till here. Well, I use all the phi's, but use the new values till here. Okay. So, and old values, of course, for the remaining ones. Okay, so that's why the symbol here is you use this file, this one. Okay, so the loop is we don't create a new array, we just rewrite on the same array. So y I comma j. Right now, this cannot be vectorized, right? Because I don't know the full array. So this is Gauss Seidel has to be a loop. Okay, so for I in loop 1 to n plus 1, j 1 to m plus 1, well 1 to m actually, but range is 1 to m plus 1, and this average. Okay, and it's basically y is updated, so that is this update operation. Okay, update and compute the error as absolute of. Okay, we need to copy, so I have this. So we keep a copy before you go in the loop, because I need to compute the error. So this is just for bookkeeping. So compute the error of the past value minus the new one. Okay, and I come here again. Okay, it turns out this is Gauss Seidel. The number of iterations required is less. This is 5000 for Jacobi and around 3000 for Gauss Seidel. So number of iterations required is basically half. However, this operation is not vectorized. So the total time taken in a computer in Python code is longer here, is in fact much longer, is not vectorized. Okay, though we are gaining in iterations, but we are losing in vectorization. So Gauss Seidel is not perfect. So what is done is red-black method. Okay, so this is the red-black method. So what is red-black method? This is for vectorization. Okay, we take alternate points. Okay, so these are the red points. You can see red points, and the black points are in between. So there are two mesh. One is red points, which are alternate points, and the black points sitting in between. Now, first, the idea is that you update red first using Gauss Seidel. We can use Gauss Seidel, use basically vectorize, so using Jacobi basically. Okay, so using Jacobi, use the red one first. But then root for then update the black using new values of red. Okay, because when I update red, this one, I'll be using when I update this black one, I'll be using these red ones. Okay, in fact, if you look at, is there in the book 4 blocks. So I used this red, and this red, and this red in one shot. Okay, then red is not done in one. Basically, I need to vectorize it. So that's one. Second will be this red, this red, this red, and this red. Then black, one black. So we are doing in 4 steps, and these 4 steps are akin to using Gauss seidel. Okay, not exactly Gauss seidel, but it works quite well. So we can vectorize this one, and it turns out number of steps required is very similar to what you get for the black dash here. Okay, is same as Gauss seidel, but time taken is very less. In fact, this is ideal. We take much less time for red black. Okay, I show in the table. So this is really good, red black. Okay, now the last one. So red black can improve even further. How do I do it? So red black or Gauss seidel. Okay, but Gauss seidel is not vectorizable, so we basically use this thing. So this is called successive relaxation. So we update it with the new values, average values, but we put a factor omega. Okay, omega is between 1 and 2. So I choose 1.5 and keep the old values as 1 minus, well, basically the 1 minus omega phi I comma j, the center values, not old values, the center values. So these are the neighbors, the 4 neighbors, this one, but this is the center value itself. Okay, and what do we get? SOR requires 1000 iterations, much less, and also less time. If I apply red black on SOR, then I get basically same steps and same number of approximately. They will be a bit different, but this requires least number of iterations SOR. But SOR, if I just do it by Gauss seidel, it will be more expensive because it cannot be vectorized. However, if I use red black SOR, successive relaxation, then I get least time, and that is sitting here. So let's see the table. This is a typo. This is 6,000. And this I didn't correct to it. So this is around 6,000. Time taken is 2.5. Gauss seidel is around 3,000. Time taken is 15 seconds. Laptop seconds. Red black is similar number of steps, 2934, and it takes 0.2 seconds, which is 1/10 of Jacobi. Okay, and much smaller compared to, or what, 75 times less than Gauss seidel. Now Gauss seidel SOR takes around 1000, and this is 7.6 seconds, and the red black SOR is 1131 seconds steps and 0.1 second. So this is the lowest time.